All right, we've got this annular cylinder. How do we want to integrate around it? Like, do we want little circles inside this washer, or what kind of shape do we want to choose? Right? What do we mean by circles? Concentric circles. Addison has a brilliant idea. I like that. We'll choose something like this. This will be our surface of integration. So, and also pretend that's a circle. So if that's our surface of integration, how much, how much volume is our little bitty, how much volume is in there, right? Right? We need to know how much volume, because what we really are interested in is how much mass is in this little dotted circle. And we know that we can get the mass by taking the density times the volume. All right, Eric, can you be a little more specific? All right, if we have some arbitrary circular shell at radius little r, how much volume, right? What can we use as an expression for this differential volume? So if we want to find the volume, the integral of the circumference of the circular shell, integral of the circumference of the circular shell is the volume. I, yes, I think you're on to it. Like, yeah, the wording is not quite right, but I get what you're saying. And yeah, the surface area of this little shell is going to be 2 pi r, right? That's the circumference of this little shell. It's going to be h thick in the into the or h tall rather in the into the screen, and then it's going to have a radial width that is equal to dr. So this is our little piece of mass that we're capturing in our little tiny shell. Okay, let's do a little cleanup there. Pull the constants out front. 2 pi h rho. And then we have r cubed dr. All right, we don't want the moment of inertia just due to this tiny piece. We want the whole thing. So the whole thing is going to be the integral of this piece here. Constants come out front. And we need to do the integral r cubed dr. And actually, we only have to integrate over the radii where there is material. So we can integrate from R1 to R2. All right. What does this integral come out to? R to the fourth over 4. Very good. Two fourths is just a half. And then when you evaluate the limits, we're going to get R2 to the fourth minus R1 to the fourth. All right, this does not look nearly as pretty as some of the other expressions that we have derived. So let's keep working on it. What's our density here? Right? Our density is mass over volume. What's the volume of this annular cylinder? Right, what's the total volume of this cylinder? That's the surface area, Matthew. Right, what's the volume, basically, of any right shape, like any regular right solid? On a room full of engineers, this should be an easy one, guys. And ladies. Let's see, someone who hasn't had much to say yet. Josue, what's the volume of a cylinder? Pi r squared h. That's exactly right. So the big cylinder, like the outer cylinder, is pi r2 squared h. But the little, like there's an empty piece in the middle. So we're going to subtract that out. Something like that. And now we can go ahead and plug that in to our result down here. So we have 1/2 pi h m over pi h r2 squared minus r1 squared times r2 to the fourth minus r1 to the fourth. That's still not great. Let's do some cancellation here. Pi's and h's cancel. So 1/2 m. At least now we've got the mass in here. But then we have r2 to the fourth minus r1 to the fourth over r2 squared minus r1 squared. I do not particularly like this bracketed bit. Can we simplify that? Right, is there a simplification we can do here? I'll give you a hint, right? Look at the form of the numerator and denominator. Yeah, Trainmaster, the top can totally factor to cancel out the denominator. To see why, let's rewrite this numerator here as r2 squared squared minus r1 squared squared. Now that is the difference of two squares when we write it that way. So we can totally write this whole thing, since if we're thinking about it as the difference of two squares, that's r2 squared minus r1 squared times r2 squared plus r1 squared over r2 squared minus r1 squared. And then we cancel out the whole denominator with this first piece here. And our final answer, the moment of inertia, is 1/2 m times r2 squared plus r1 squared. Yep, good job, Roberto and Trainmaster. That's a tricky one to see, but it looks so much better when we've simplified it in this way. So there's an annular cylinder. You have any questions or comments on this calculation? Just as a reminder, one of the final exam questions will 100% be a moment of inertia integral. Okay, so we've got a whole lot of silence, which means everybody is fine with these integrals, right? And there's going to be no trouble at all on the final. An interesting integral. Yes, it is. I think you start to see why I enjoy these questions so much. Like these are really interesting integrals. Once you have calculus 2 methods, right? I'm thinking specifically like there's a section in the second semester of calculus where you do an integral to find the area between two arbitrary curves. And once you've got that sort of method down, there's nothing stopping you from calculating the moment of inertia for arbitrarily shaped pieces. Uh, Now, in practice, when you're in your professional jobs, you're just going to have SolidWorks do this for you. But if you don't know what's going on behind the scenes, you won't know when SolidWorks spits out a bad answer. Which it does because, you know, people are fallible and they input, you know, wrong stuff all the time. So it's good to have a kind of software bullshit detector so that you know when something is not quite right. All right. Let's talk about momentum. So when we first started talking seriously about rotation, we started with Newton's second law. And we went to rotation by cross multiplying both sides of the equation by the radius. So if we have some curved motion that's undergoing here, there is some radius of rotation, radius of curvature here. And so we take the cross product of both sides with respect to the radius. So we get sum of r cross f equals r cross ma. And cross products are a bit finicky to work with. So we made use of this identity that says that the magnitude of two vectors, A cross B, is going to be magnitude of A times magnitude of B times the sine of the angle between A and B. So if we've got A like so, and we've got B like so, then the angle between them is like that. And the other thing that we know is that A cross B is actually a vector. So A cross B is always going to be perpendicular to A, and it's going to be perpendicular to B. Which means that if A and B define kind of the plane that we're working in, A cross B defines the space that we're working in. So A cross B is going to be coming out of the page. But still, that lets us simplify this this sum. So now it's the sum of r times f equals MRA. And then we thought about our rotational coordinates. And, you know, if this is R and this is S, then in radians, the definition of our angle is the ratio S over R. So then our angular speed is the derivative of that, ends up being the velocity over the radius, and our angular acceleration ends up being a over the radius. So we use this analysis here to rewrite Newton's second law in terms of rotational coordinates. And then we made the definition that for a point, this is the moment of inertia. And this we called torque. And so the rotational form of Newton's second law is the sum of torques equals I times alpha. Any comments or questions on this brief review? We talked about this about a week and a half ago. Torque. And then, yeah, when we have a sum of those, it's torques. Eric, I do like your spelling better, but this spelling is traditional. Using this definition, we were able to get a rotational equivalent for kinetic energy as well. So our rotational kinetic energy is 1/2 times the moment of inertia times the square of the angular speed. One thing we weren't able to get, at least so far, is something equivalent to momentum in rotation. So if you remember, we when we were talking about momentum, we started with Newton's second law. We realized that acceleration is the change in velocity over time. So we have dv dt. Since m in most cases is a constant, so we have no trouble bringing that inside the derivative. So it's the derivative of mv dt. And this motivated us to define the things inside the parenthesis there as momentum. So force is equal to derivative of momentum with respect to time. We have not so far achieved an angular analog to this version of Newton's second law. There is a straightforward way to go about it, though. Let's start by looking at what the cross product of r and momentum look like. Remember, this is how we started off analyzing Newton's second law. So we took the cross product of both sides of Newton's second law with respect to r. We're going to do the same thing here. So r cross p, we're going to call this L for the moment. L is traditional. All right. Let's take a look at what this looks like. We can use our same kind of trick that we used last time if we only want to talk about the magnitude of these. So we can say the magnitude of L is equal to RP sine theta. And P, of course, is m times v. So we have R mv sine theta. And since we kind of want to go into rotational coordinates, that's what motivated this whole thing here. Instead of v, let's write down, let's use the angular version here. So then v equals omega times r. So we can write this as m omega r squared. Everyone with me so far? Let's take the time derivative of this. What inside the parentheses there actually changes with time? Right? We've got 4 quantities inside the parentheses. Like, which ones are constant and which ones actually change with time? Theta, actually, you know what? I should not be using theta here. We're using theta for the angular coordinate. The angle here that we want is actually the angle between r and p. So if this is r and this is p, we will use beta here. Good catch. I should have been more careful with my variables. So beta presumably does not change. Does the mass of our object change with time? Right? No, the mass normally does not change with time. Does the radius change with time? Yeah, Addison, omega definitely might change with time, right? If we have some acceleration. So if we have some angular acceleration, we definitely might have a change in omega, which would give us this term, right? So m r squared sine beta alpha. If the radius is also changing, then product rule tells us we actually need a second term. Everyone with me so far? All right. If, for the moment, let's ignore this second term. Or let's say that the radius is not changing. If the radius is not changing, then what does this term actually look like? Right? This is mr squared. And this thing right here, well, that's just I alpha. So the sine beta exists to give us just the part of this term that is perpendicular to the radius. So if we, so suppose that we're only we're going to, on the front end, deal with any momentums and forces, so that we're only dealing with the orthogonal component of the momentum, right? So we could always divide this up into a part that is perpendicular and a part that is parallel. If we do that and we only deal with the perpendicular parts, we don't have to worry about these sine betas, because beta is going to be 90 degrees. And then this term here, like, this is exactly what we meant by sum of torques. So that lets us write down, like, hey, the sum of torques is equal to, right, the time derivative of L, and that is really similar to the way that we wrote down momentum, like linear momentum in terms of forces. And because of this, we call this term L, we call this the angular momentum. could also have come at this from the other end. If the sum of torques equals I alpha, this is Newton's second law for rotation, we could have said, well, this is like I d omega dt, right? And then the same sort of thing that we did for linear momentum. Right? And then renamed this thing in the parentheses angular momentum. And just like the momentum version of Newton's second law, in linear space, this ends up being a much more general form. So we actually have, so in the linear case, we have sum of forces equals dp dt, and we will frequently prefer this version of Newton's second law, because if mass is constant, this reduces down to F equals ma. If mass is not constant, like for rocket engines, it allows us to analyze that too. And in the same way, we will prefer frequently to say sum of torques equals dl dt. If the moment of inertia is constant, then this just reduces to sum of torques equals I alpha. But if the moment of inertia is not constant, that allows us to analyze that too. All right. Do we have questions or comments?